carrier. On this, the work part will be located, and this in between one, it is the stationary fixed one, and this is the transfer beam. One transfer beam will be there, and one fixed beam will be there, and the work part carrier will be there. And here they have provided the notch. In this notch, the extended part of the work part holder will be located, and how it works is this particular beam will be lifted up, and again it will be moved front by means of some pneumatic or hydraulic cylinder, so that it is moving. This particular moving boom is moving like this, one by one. It carries the work part, and this work part will be located in the work part holders. Okay, as the name indicates, walking beam transfer mechanism, this will be a linear mechanism. This is used to transfer the work part from one station to the other station by means of this. And here one beam will be fixed, the other beam will be movable. On this fixed beam, the work part will be located, and you can see that this is a fixed beam. This is fixed to the table, and this particular transfer beam will be lifted up. Once it is lifted, it is holding the work part, and again it is moving front, and again it will come down. So up, front and down. While doing like this, the work part will be moving progressively like this, one by one, but the transfer beam will be moving up to this extent, and again it will be coming back. Okay, and the one limitation is that it cannot be used for meters together. It is very smaller movement it will be used. Okay, it is a simple mechanism. And another disadvantage is that this particular work part holder and all these notches will be specifically done for a particular job only. It cannot be changed. This work holder cannot be changed for some other product suddenly. So that what happens, the work part holder will be used. In this, whatever the shape of the work part may be, that will be located. So this is what the walking beam transfer mechanism. You understood? As shown in figure, the walking beam transfer mechanism consists of work part holder, fixed beam and transfer beam. And the fixed beam is fixed to the table. The transfer beam will be having the notches, and the work part holder is having the notches, and the passion of movement will be moving up, moving front and getting down. So by doing this, what happens, the work part will be moving from one station to the other station. So this will be specifically used for small components. And this disadvantage, the advantage is it is very simple in nature, and the maintenance cost is very less, and the low investment, and it is fixed beam, the fixed one. It cannot be changed or to some other type of productions. The limitations are the length of it is restricted. It cannot be used for meters together. It will be used for only few feet. Okay, and the other limitation is that it cannot be changed out to some other type. See, the transfer, the distance cannot be changed. It will be fixed. Okay, and this is one linear type of mechanism. And now let me come to the Geneva mechanism. Already you know this type of the wheel you have seen anywhere. Have you seen this? In the shaping machine you can see this Geneva mechanism. Okay, the Geneva mechanism, it is a rotary indexing mechanism actually. And here for this 360-degree, and here I have shown 4 slots. The 4 slots indicates 4 stations. Okay, so 360 divided by 4, it gives you 90-degree. So for each one stroke, it will be rotating, advancing by 90-degree. So this will be useful for 4 stations. And if you want, you can go for the 8. And if you want, you can go for the 12. If you want, you can go for the 3, like that. Okay, and the minimum slots can be provided will be 3. Okay, and 120-degree apart, and maximum can be up to 12. Okay, this is a Geneva mechanism, and this Geneva mechanism is one other mechanism. This is used for rotary indexing table. So in the previous class I have discussed about the rotary indexing table, and if there are 8 workstations, that means every integrate the fraction of rotation it has to advance by 45 degree. 360 divided by 8, it will be giving you 45 degree. So like that. Okay, if it is for the sixth rotation, then 360 divided by 6, it will be 60-degree rotation. Okay, this Genoa mechanism will be used for the indexing the tables. That's all. It is used for the indexing the table, and here you will get some problems. Okay, you will get some problems. You will get some problems, and the TC, the cycle time is equal to 1 by n number of rotations. For example, in this case, I have 4 slots. That means 4 stations. So one TC is equal to 1 by 4. Okay, and the TS, it is the available or dwell time. Dwell time or available time. See, this is the dwell or available time. Even though it is rotating, the table, see, continuously this Genoa mechanism will be rotating. While it is rotating, this from here, this point to this point, while it is rotating, it will be a dwell time. This dwell time for this particular cam will be indicating the cycle time for the machines, working station. Well, even though it is rotating, it is not rotating the Genoa mechanism. That means to say that particular time will be utilized for the cycle time for the workstation. Okay, workstation. And this available or servicing time or dwell time is equal to TS is equal to 180 plus theta. Theta indicate in this case it is 45 degree divided by 360 degree into number of rotations n. That will be giving you TS. So please remember, dwell time or available time is equal to 180 degree plus theta divided by 360 into n. And the available servicing or processing time. So this servicing or processing time is the time which is required to move the work part from one station to the other station. That means the amount of time it has been taken to move from this particular position to this particular position, that will be 180 degree minus theta divided by 360 into n. That is a transfer time. This is the servicing time. TS is equal to 180 degree plus theta divided by 360 into n, and transfer time is, our servicing time is equal to 180 minus theta divided by 360 into n. Okay, did you understood? Very simple one case. And here I have taken a simple example. Please look here. A rotating work table is driven by a Genoa mechanism. See, please look here. The earlier had taken you to the indexing table. Okay, there are two methods by which the work part can be transferred. One is a linear, other is a rotary. The rotary table, it will be fixed with the Genoa mechanism. That's all. Okay, a rotary work table is driven by a Genoa mechanism with 6 slots. That means 6 workstations can be accommodated. A driver rotates at 3 degree revolutions per minute. The driver rotates at 360 RPM. Find the cycle time, available processing time, and last time each cycle to index the table. Okay, and the cycle time is the 1 by n, that is TC is equal to 1 by n, that is 22 seconds. And the angle of rotation, already you know that there are how many 6 workstations. That means 360 divided by 6, it will be 60 degree is the angle of rotation. Angle of rotation of the Genoa mechanism. And the servicing time is equal to 180 plus 60 divided by 360 into 30. The 30 is the rotation, and the transfer time is 180 minus theta divided by 360 into n. That is 60, and this will be 30. So these are the 1.333 second and 0.667 second. And you can see that the servicing time will be always greater than the transfer time. The transfer time is only, it will be transferring, it will be rotating by 60 degree in this particular time, and this is the dwell time. In this, the whole cycle will be operated. Is it clear to you, that problem? TC is equal to 1 by n. Theta is equal to 360 divided by the number of slots. Okay, and TS is equal to 180 plus theta divided by 360 into n, and transfer time is 180 minus theta divided by 360 into n. Okay, and this minute I have converted into second by multiplying with 60. Did you understood this problem?
Yes, sir.
Okay, very simple problem. Very simple problem. Now, buffer storage or storage buffer, in this only a sub part, sub one. In all these linear transfer systems, linear automated systems, in between the workstations, I told you already, there may be so many reasons for which the storage buffer will be accommodated. One is the non-uniform cycling time, non-uniform operation time of workstations. One thing. The second one, to avoid the blockage of station and blockage of station and starving of station. Blocking of station and starving of station. To avoid this, what happens are some of the workstations have come for the maintenance in between. That particular time, the part which is required for the other machines can be given by a stored buffer stockage. The meaning of the storage buffer is that in between the two workstations, a particular type of atomized, the automated storage system will be provided that will be storing the extra parts which will be required frequently by the next machine when the previous machine has come for the maintenance, or if cycle time is minimum or maximum. Due to variation in the cycle time also, sometimes some of the products have to be stored, so that storing can be done by the storage buffer. The storage buffer is not a manual method, not simply dumping all the material by manually. It is not. It is automatically the extra material will be loaded into the storage buffer, and whenever it is required, automatically the stored material will be retrieved from the storage buffer and it will be put into the conveyor automatically by means of automated device. So this is what is called as a storage buffer. And what are the why we are going to have the storage buffer? The basic reasons are to reduce the impact of workstation breakdown. As just now I told, if there is a breakdown in the workstations, so due to this, what happens? The next machine will be suffering due to the lack of materials. So that time the storage buffer will be providing automatically. And the next one is to provide a bank of parts to supply the line. So that means automatically in the manufacturing systems, this particular parts will be supplied automatically. The next point, to provide a place to put the output of the line. Okay, so it is out of our discussion now, to provide a place to put out of line. Okay, and to allow for curing time or other processing delay. Okay, curing time and other processing delay. So here a design is made to provide a sufficient time curing to occur before supply of the part to the next station. So not only to provide or to satisfy the starving of station and blocking of station, while the material is moving from one station to the other station. For example, I have done welding in one station. So suddenly, if I have to get to the next station, some amount of curing time have to be given so that it will be cooled down, or some painting has been done, or galvanizing has been done on one part. So some amount of curing if you have been given. So while it is going to the next station, what happens? The paint will be disturbed. So during this case, what happens? Simply it will be letting into the storage buffer, and again it will be taken to the downstream and it will be taken to the upstream. That means onto the conveyor automatically. So by the time it is taking the rotation, some amount of time will be consumed so that it will become a curing time. Okay. So to reduce the impact of workstation, to provide a bank of part for supply of line and allow the curing time or the other processing times. The next one, smooth cycle time variations. So smooth cycle time variation, as I told you, all the workstations need not to have same working cycle. There will be variation in the working cycle. So to compensate this variation in the working cycle, to balance the line, these buffer storage units will be used. So kindly note down this buffer storage. It is short, write a short notes on buffer storage, and write the reasons for having the buffer storage. These are the reasons.